Hello there, so welcome back to the channel and welcome to Excel Island, where the goal and objective is to learn and master Python over the next 100 days. Today is day 77. We're going to continue from where we stopped on day 76. Yep, let me just double check. Yeah, on the 76, we're actually looking at the fundamentals of hypothesis testing in Python. Today, we're looking at two sample and another test in Python. So without any other delay, let's continue from there and move on. So all data sets exercise files will be linked under the YouTube description, so you can also download and practice yourself. This was hypothesis testing in Python, chapter 1. Let's move to chapter 2.
In the previous chapter, we calculated the z-score, which was a test statistic for a single variable. Here, we'll look at a related problem of comparing sample statistics across groups in a variable. In the Stack Overflow dataset, converted comp is a numerical variable of annual compensation. Age first code cut is a categorical variable with two levels, child and adult, which describe when the user started programming. We can ask questions about differences in compensation across the two age groups, such as, are users who first programmed as a child better compensated than those that started as adults? The null hypothesis is that the population mean for the two groups is the same, and the alternative hypothesis is that the population mean for users who started coding as children is greater than for users who started coding as adults. We can write these hypotheses using equations. Mu represents an unknown population mean, and we use subscripts to denote which group the population mean belongs to. An alternate way of writing the equations is to compare the differences in population means to 0. 0 here corresponds to our hypothesized value for the difference in means. To calculate summary statistics for each group, we start with the sample, group by the categorical variable, and then compute on the numeric variable. A pandas way of doing this is shown, calculating the mean of the converted comp column after grouping by age first code cut. Here, the child programmers have a mean compensation of $132,000, compared to around $111,000 for adult programmers. Is that increase statistically significant, or could it be explained by sampling variability? Although we don't know the population mean, we estimate it using the sample mean. X bar is used to denote a sample mean. Then we use subscripts to denote which group a sample mean corresponds to. The difference between these two sample means is the test statistic for the hypothesis test. The z-scores we saw in chapter 1 are a type of standardized test statistic. Z-scores are calculated by taking the sample statistic, subtracting the mean of the statistic as the population parameter of interest, then dividing by the standard error. In the two-sample case, the test statistic, denoted t, uses a similar equation. We take the difference between the sample statistics for the two groups, subtract the population difference between the two groups, then divide by the standard error. To calculate the standard error needed for the denominator of the test statistic equation, bootstrapping tends to be a good option. However, there is an easier way to approximate it. We calculate the standard deviation of the numeric variable for each group in the sample, and the number of observations in each group. Then enter those values into the equation and compute the result. Here's the test statistic equation again. If we assume that the null hypothesis is true, there's a simplification we can make. The null hypothesis assumes that the population means are equal, and their difference is 0. So the population term in the numerator disappears. Inserting the approximation for the standard error, We now have a way of calculating the test statistic using only calculations on the sample dataset. We need the mean, standard deviation, and number of observations for each group to fill in the formula for t. We again use group by and method combinations with mean, std, and count. Assigning the values to 6 different variables, the numerator is a subtraction of the sample means, and the denominator is like a weighted hypotenuse. The t-statistic is around 1.87. Just as with z-scores, we can't draw any conclusions yet. For that, we'll need to wait for the next video. In the meantime, let's calculate some test statistics.
Okay, let's calculate some test statistics. As the hypothesis testing workflow. You've seen the hypothesis testing workflow for one sample case where you compare the sample mean for hypothesized value and the two sample case where you compare two sample means. In both cases, the workflow share common steps. So place the hypothesis testing workflow steps in order from the first to last. So hypothesis testing from first to last. Okay, let's see that. Compare the hypothesis first thing from first to last. So looking at it a little bit further, you need to perform two sample problems. So the first is to compare and identify the obtained parameter to hypothesize about, then specify the null hypothesis and alternative hypothesis, then determine, standardize, followed by measure of evidence, followed by interpreting and conduct hypothesis test in Python. Ooh, must have missed that for each other. Oh, voila, we know this. So conduct hypothesis test in Python and do that. Why workflow? Regardless of the type of hypothesis test you are performing, you should have a workflow that follow this format. Two sample mean statistics. Okay. So calculate the numerator of the t-test statistics. So we know that two hypothesis tests for determining if there's a difference between the mean or superpopulation use a different type of test statistics to the z-score you saw in chapter 1. It is called t and it is called c, and it can be calculated from three values from each sample using this equation below. Okay, let's do that. Calculate numerator of the test statistics, denominator, and so on and so forth. So numerator should be x bar, and denominator should be a function of np square roots. Then you just do the numerator by the denominator to get your t stats. Let's see if you're correct. And voila, we nailed it. Let's submit and see. Voila, we nailed it then. Okay. Let's see if we can perform the same calculation in Jupyter Notebook here. S bar is not defined, so we need to know how to import this X bar. Okay, moving on though. Let's see calculating p-values from two statistics.
In the previous lesson, we calculated the test statistic t. The test statistic t follows a t-distribution. T-distributions have a parameter called the degrees of freedom, or df for short. Here's a line plot of the PDF of a t-distribution with 1 degree of freedom in yellow, and the PDF of a normal distribution in blue dashes. Notice that the t-distribution for small degrees of freedom has fatter tails than the normal distribution, but otherwise they look similar. As we increase the degrees of freedom, the t-distribution gets closer to the normal distribution. In fact, a normal distribution is a t-distribution with infinite degrees of freedom. Degrees of freedom are defined as the maximum number of logically independent values in the data sample. That's a fairly tricky concept, so let's try an example. Suppose our dataset has 5 independent observations, and that 4 of the values are 2, 6, 8, and 5. Suppose we also know the sample mean is 5. With this knowledge, the 5th value is no longer independent. It must be 4. Even though all 5 observations in the sample were independent, because we know an additional fact about the sample, that it has a mean of 5, we only have 4 degrees of freedom. In our 2-sample case, there are as many degrees of freedom as observations, -2, because we know 2 sample statistics, the means for each group. Recall the hypotheses for our Stack Overflow question about compensation for the 2 age groups. Since this is a greater than alternative hypothesis, we need a right-tailed test. We're going to calculate a p-value in a moment, but we first need to decide on a significance level. There are several possibilities. Let's use 0.1. That means that we reject the null hypothesis in favour of the alternative if the p-value is less than or equal to 0.1. In Chapter 1, to get the p-value, we transformed the z-score with the normal CDF. Since it was a right-tailed test, we subtracted the result from 1. In the previous video, we used an approximation for the test statistic standard error using sample information. Using this approximation adds more uncertainty, and that's why this is a t instead of a z problem. The t-distribution allows for more uncertainty when using multiple estimates in a single statistic calculation. Here, the multiple estimates correspond to the sample mean and the sample standard deviation. Now we are calculating means rather than proportions. The z-score is replaced with a t-test statistic. This is the value calculated in the previous video. The calculation also needs the degrees of freedom, which is the total number of observations in both groups minus 2. To calculate the p-value, we need to transform the test statistic using the t-distribution CDF, instead of the normal distribution CDF. Notice the use of t.cdf instead of norm.cdf, and that the df argument is set to the degrees of freedom. This p-value is less than the significance level of 0.1, so we should reject the null hypothesis in favour of the alternative hypothesis that Stack Overflow data scientists who started coding as children earn more. While I re-evaluate my own childhood and wonder why I didn't start programming earlier, time for you to do some exercises.
That's a good analysis. I should have started programming earlier. I will definitely aim more. Why is still needed? The process for calculating p-value is to start with the sample statistics, standardize it to get a test statistic, then transform it via cumulative distribution function. Chapter 1, that final transformation was noted z, and the CDF transformation used the standard z distribution. In the last video, test statistics was denoted t, and the transformation used the t distribution. In which hypothesis testing scenario is still distribution needed instead of the z distribution. Interesting. So if you're using a sample standard deviation to estimate the standard error is computationally easier than using the bootstrapping. However, to correct for the approximation, you need to use t-distribution when transforming the test statistics to get the p-value. Interesting. Okay. Let's talk about the t-distribution. The t-distribution. Okay, now we can just change this one here. Which statement about the t-distribution is true? That should be a decrease, an increase. Exactly. Tip topic. The normal distribution is essentially a t-distribution with infinite degrees of freedom. So an increase, as you increase the degree of freedom, the t-distribution, PDF and CDF curves get closer to the normal distribution. So you increase the degree of freedom, you get closer to the normal distribution. You can see it is getting closer. Okay, interesting. From T to top to P. So the question is, which type of test does the alternative hypothesis indicate that we need? We call the hypothesis the mean weights. Okay. We call the hypothesis that the mean weight of shipment that went late is the same as the mean weight of shipment that were late. Okay, we're going to use the left tail then. Okay. Now let's calculate the degree of freedom for the t-test and copy the p-value. So we need to calculate degrees of freedom, then calculate the p-value. When you calculate the p-value from there, we use it c.cdf, then set it to degree of freedom. Oh, there's an error in my p-value there. Oh, why must it get an error in this instance? Wait an import from Cypher import stats. Oh, oh, under error again. Oh, what could be the error here? Oh, oh, how are we getting this error? Let's see the answer. Oh, definitely what we needed to do. Okay, finally, it now says, what decision should you make based on the results hypothesis? Oh, that definitely is. So let's look at paired tests, paired tests.
Previously, we used the t-distribution to compute a p-value from a standardized test statistic related to the difference in means across two groups. Here's a dataset of US presidential elections. Each row represents a presidential election at the county level. The variables in the dataset are the US state, the county within that state, and the percentage of votes for the Republican candidate in 2008 and in 2012. One question is whether the percentage of votes for the Republican candidate was lower in 2008 compared to 2012. To test this, we form hypotheses. As before, the null hypothesis is that our hunch is wrong, and that the population parameters are the same in each year group. The alternative hypothesis is that the parameter in 2008 was lower than in 2012. Let's set a significance level of 0.05. One feature of this dataset is that the 2008 votes and the 2012 votes are paired, which means they aren't independent, since they both refer to the same county. This means voting patterns may occur due to county-level demographics and local politics, and we want to capture this pairing in our model. For paired analyses, rather than considering the two variables separately, we can consider a single variable of the difference. This is stored in a data frame called sample data, with a column named diff. In this histogram of the difference, most values are between -10 and 10, with at least one outlier. The sample mean, x bar, is calculated from this difference. It is around -2.88. We can restate the hypotheses in terms of the single population mean, mu diff, being equal to or less than 0. The test statistic t has a slightly simpler equation compared to the two-sample case. We have one statistic, so the number of degrees of freedom is the number of pairs minus 1. To calculate the test statistic, we need the number of rows in the dataset, 100, and the standard deviation of the differences. We already calculated x bar diff, the mean of the differences, as -2.88. Assuming the null hypothesis is true means mu diff is 0. We now have everything we need to plug into the equation to calculate t. It's -5.6. The degrees of freedom are 1 less than n diff at 99. Finally, we transform t with the t-distribution CDF. The p-value is really small, at around 9.6 times 10 to the -8. That means we reject the null hypothesis in favour of the alternative hypothesis that the Republican candidates got a smaller percentage of the vote in 2008 compared to 2012. That was a lot of calculating. Fortunately, there's an easier way. The Penguin package provides a variety of different methods for hypothesis testing and returns the results as a pandas data frame. Its output can be a little friendlier to work with than similar methods from scipy.stats. One method from Penguin is t-test, and it works with array-like objects, so the first argument is the series of differences. For a converted one-sample test like this, y specifies the hypothesized difference value from the null hypothesis, which is 0. The type of alternative hypothesis can be specified as two-sided, less, or greater, corresponding to two-tailed, left-tailed, and right-tailed tests, respectively. Here's the output. We can recognize the value of the test statistic, the degrees of freedom, the alternative direction, and the p-value. The additional output refers to more advanced statistical concepts that are outside the scope of this course. There's a variation of t-test for paired data that requires even less work. Rather than calculating the difference between the two paired variables, we can just pass them both directly to t-test as x and y, and set paired to true. Notice that the results in the first 4 columns are the same as before. If we don't set paired to true, and instead perform an unpaired t-test, then the numbers change. The test statistic is close to 0. There are more degrees of freedom, and the p-value is much larger. Performing an unpaired t-test when our data is paired increases the chances of false negative errors. Time to perform some pairing.
Okay, let's do some pairing. Paired, not paired. Okay. So the t-test is paired needed. The t-tests are used to compare two sample means. However, the test involves different calculations depending upon whether the two samples are paired or not. To make sure you use the correct version of the t-test, you need to be able to identify pairing. Okay. So pairs to test the fitness of a new elementary school study technique. Pre and post tests are given to the same random sample, so they're not paired. Okay. So create a new div column containing percentage, sample them data.div, oh, okay. They calculate the mean difference for the column of x bar. And you calculate standard deviation of the different column as ST standard deviation. And finally, plot the histogram of the difference with 20 bins. Voila. So, what is the definition of the same result? Stressing. And finally, using the t-test, let's conduct a t-test sample difference. Let's see. Oh, and two-sided. Okay, then finally, what is the correct decision from the t-test, assuming this is equal to 0.1? Reject the null hypothesis. We need to conduct peer tests on the democratic vote. Interesting stuff. It's missing one C there. Oh, okay. Voila, we know it. And finally, from this result, compare the peer test to an appropriate compared test on the same data. That should give us the p-value from unpaired test equals to the p-value. So the p-value from the unpaired test is greater than that for the p-value from the paired test. Interesting. Let's look at ANOVA tests.
We've seen how to compare two groups in the unpaired and paired cases. But what if there are more than two groups? The Stack Overflow survey includes a job satisfaction variable, with 5 categories from very satisfied down to very dissatisfied. Suppose we want to know if mean annual compensation is different for each of the levels of job satisfaction. The first thing to do is visualize the distributions with box plots. Seaborn's box plot method provides a nice option here, with converted comp on the horizontal axis and job sat on the vertical axis, using the Stack Overflow data. Very satisfied looks slightly higher than the others, but to see if they are significantly different, we'll need to use hypothesis tests. ANOVA tests determine whether there are differences between the groups. We begin by setting our significance level to 0.2. This value is larger than in many situations, but will help us understand the implications of comparing different numbers of groups later on. We use the Penguin ANOVA method to compare values across multiple groups. We specify the data as Stack Overflow, the dependent variable, dv, as converted comp, and the column of groups to calculate between as job sat. The p-value is stored in the p-unc column, which is 0.0013, which is smaller than alpha at 20%. That means that at least 2 of the categories of job satisfaction have significant differences between their compensation levels. But this doesn't tell us which 2 categories they are. To identify which categories are different, we compare all 5 job satisfaction categories, testing on each pair in turn. There are 10 ways of choosing 2 items from a set of 5, so we have 10 tests to perform. Our significance level is still 0.2. To run all these hypothesis tests in one go, we can use pairwise tests. The first 3 arguments of data, dv, and between are the same as the ANOVA method. We'll discuss p-adjust shortly. The result shows a data frame where A and B are the 2 levels being compared on each row. Next we look at the p-unc column of p-values. 3 of these are less than our significance level of 0.2. In this case, we have 5 groups, resulting in 10 pairs. As the number of groups increases, the number of pairs, and hence the number of hypothesis tests we must perform, increases quadratically. The more tests we run, the higher the chance that at least one of them will give a false positive significant result. With a significance level of 0.2, if we run one test, the chance of a false positive result is 0.2. With 5 groups and 10 tests, the probability of at least one false positive is around 0.7. With 20 groups, it's almost guaranteed that we'll get at least one false positive. The solution to this is to apply an adjustment to increase the p-values, reducing the chance of getting a false positive. One common adjustment is the Bonferroni correction. Looking at the p-core column corresponding to corrected p-values, as opposed to the p-unc column for uncorrected, only 2 of the pairs appear to have significant differences. Penguin provides several options for adjusting the p-values, with some being more conservative than others. No adjustment with none is the default, but in almost all pairwise t-testing situations, choosing a correction method is more appropriate. Let's run lots of tests.
Okay, let's go lot of tests. Visualizing many categories. We have to go list shipment by shipment mode and calculate the mean pack price for it. And that will have to do with, so for this chapter, we only consider the case of differences in numeric variable between two categories of, of course, many datasets contain more categories. For you get conducting tests on many categories, it's often able to perform exploratory data analysis, calculating some statistics for each group. Okay, let's do that. And we use a group list statement by shipment date and calculate the standard deviation pack price for each group. Waiting for this to complete loading. Let's print this first one. Then let's create a box plot for shipments. Oh, simple box plots. Interesting. And finally, run an ANOVA on the late shipment investigation of pack price. Conducting an ANOVA test. Okay, now say assuming the syntax level is 0.1, should you reject the null hypothesis that there is no difference between pack price between shipment modes? Imagine over there is a significant difference in pack price between the shipment modes. However, we don't know which shipment modes this applies to. Okay. Then finally we have to pair tests. Perform a pairwise test pack on the price. Let's do that. What should be the result then? Super simple. Modify the pairwise test. Use the Boniforme p-value. Okay. So this is the result. Penguin pairwise test. Let's run the code and see and submit. And finally, in the bona fide correction results and assuming a similar level of 0.1, for each pairs of shipment modes should you reject the null hypothesis? So that should be number one then. Pairwise perfection. After applying the Bufferoni adjustment, the p-value for the t-test between each of these three groups are all less than 1. Interesting. Well, we finished chapter 2. Let's go to chapter 3 and complete it also, which is the proportion test.
Let's return to thinking about testing proportions, as we did in Chapter 1. The hypothesis tests in
This was chapter 3. One sample proportional text. Let's see.
Chapter 1 measured whether or not an unknown population proportion was equal to some value. We used bootstrapping on the sample to estimate the standard error of the sample statistic. The standard error was then used to calculate a standardized test statistic the z-score, which was used to get a p-value, so we could decide whether or not to reject the null hypothesis. A bootstrap distribution can be computationally intensive to calculate, so this time we'll instead calculate the test statistic without it. An unknown population parameter that is a proportion, or population proportion for short, is denoted p. The sample proportion is denoted p hat, and the hypothesized value for the population proportion is denoted p0. As in Chapter 1, the standardized test statistic is a z-score. We calculate it by starting with the sample statistic, subtracting its mean, then dividing by its standard error. P hat minus the mean of p hat divided by the standard error of p hat. Recall from sampling in Python that the mean of a sampling distribution of sample means, denoted by p hat, is p, the population proportion. Under the null hypothesis, the unknown proportion p is assumed to be the hypothesized population proportion, p0. The z-score is now p hat minus p0 divided by the standard error of p hat. For proportions under h0, the standard error of p hat equation can be simplified to p0 times 1 minus p0 divided by the number of observations, then square rooted. We can substitute this into our equation for the z-score. This is easier to calculate because it only uses p hat and n, which we get from the sample, and p0, which we chose. We might wonder why we used a z-distribution here, but a t-distribution in Chapter 2. This is the test statistic equation for the two-sample mean case. The standard deviation of the sample S is calculated from the sample mean x bar. That means that x bar is used in the numerator to estimate the population mean, and in the denominator to estimate the population standard deviation. This dual usage increases the uncertainty in our estimate of the population parameter. Since t-distributions are effectively a normal distribution with fatter tails, we can use them to account for this extra uncertainty. In effect, the t-distribution provides extra caution against mistakenly rejecting the null hypothesis. For proportions, we only use p hat in the numerator, thus avoiding the problem with uncertainty, and a z-distribution is fine. Returning to the Stack Overflow survey, let's hypothesize that half of the users in the population are under 30, and check for a difference. Let's set a significance level of 0.01. In the sample, just over half the users are under 30. Let's get the numbers needed for the z-score. P hat is the proportion of sample rows where age cat equals under 30. P0 is 0.5 according to the null hypothesis. N is the number of rows in the dataset. Inserting the values we calculated into the z-score equation yields a z-score of around 3.4. For left-tailed alternative hypotheses, we transform the z-score into a p-value using norm.cdf. For right-tailed alternative hypotheses, we subtract the norm.cdf result from 1. For two-tailed alternative hypotheses, we check whether the test statistic lies in either tail, so the p-value is the sum of these two values, one corresponding to the z-score and the other to its negative on the other side of the distribution. Since the normal distribution PDF is symmetric, this simplifies to twice the right-tailed p-value, since the z-score is positive. Here, the p-value is less than the significance level of 0.01, so we reject the null hypothesis, concluding that the proportion of users under 30 is not equal to 0.5. Let's try an example.
Okay. Hmm. Let's see. The t-test is needed for tests of means since you are estimating to unknown quantities, which leads to more variability. Well, now let's hypothesize that proportion of late shipment by 6%. Calculate sample proportion. We're going to use the length to count the length sample size for late shipments. Okay. Next to calculate numerator. Numerator is going to be this. Okay, that's then there's this because that's going to be numerator divided by denominator. Okay, going to some error. Oh, oh, am I missing? Define is to transform the z-score value into this. This is by no one norm. So to transform the z-score value, 1 minus num dot cdf score. Oh, interesting. Those are two sample proportion tests.
Great work so far. In the previous lesson, we tested a single proportion against a specific value. As with means, we can also test for differences between proportions in two populations. The Stack Overflow survey contains a hobbyist variable. The value yes means the user described themselves as a hobbyist, and no means they describe themselves as a professional. We can hypothesize that the proportion of hobbyist users is the same for the under 30 age category as the 30 or over category, which is a two-tailed test. More formally, the null hypothesis is that the difference between the population parameters for each group is 0. Let's set a significance level of 0.05. Here is the z-score equation for a proportion test. Let's break it down. The sample statistic is the difference in the proportions for each category. That's the two p-hat values in the numerator. We subtract the hypothesized value of the population parameter, and assuming the null hypothesis is true, it's 0. The denominator is the standard error of the sample statistic. We can again avoid having to generate a bootstrap distribution to calculate the standard error by using a standard error equation, which is a slightly more complicated version of the one sample case. Note that p-hat is a weighted mean of the sample proportions for each category, also known as a pooled estimate of the population proportion. P-hat can be calculated using the following equation. This looks horrendous, but Python is great at handling arithmetic. We now only need 4 numbers from the sample dataset to perform these calculations and calculate the z-score, the proportion of hobbyists in each age group, and the number of observations in each age group. To calculate these 4 numbers, we group by the age category and calculate the sample proportions using .value counts, and the row counts using .count. As we're looking at the proportion of hobbyists, we'll only be focusing on rows where hobbyist is yes. To isolate the hobbyist proportions from p-hats, we can use Panda's multi-index subsetting, passing a tuple of the outer column and inner column values. This returns a sample proportion of 0.77 for the at least 30 group and 0.84 for the under 30s. The number of observations in each age category can be extracted with simpler Pandas subsetting. There are 1,050 rows in the at least 30 group and 1,211 for the under 30 group. After that, we can do the arithmetic using our equations for p-hat, the standard error, and the z-score to get the test statistic. This returns a z-score of -4.22. Luckily, we can avoid much of this arithmetic. The proportions z-test function from stats models can calculate the z-score more directly. This function requires 2 objects as numpy arrays: the number of hobbyists in each age group and the total number of rows in each age group. We can get these numbers by grouping by age cat and calling .value counts on the hobbyist column, as shown above. The numbers can then either be read off or subsetted to create the arrays. Next, we import proportion z-test from statsmodels.stats.proportions and pass the arrays to the count and nobs arguments. Because we're testing for a difference, we specify that this is a two-sided test, using the alternative argument. Proportion z-test returns a z-score and a p-value. The p-value is smaller than the 5% significance level we specified, so we can conclude that there is a difference in the proportion of hobbyists between the two age groups. Time to perform your own proportion tests.
Okay. So let's calculate proportion test. So the proportion of the two tests. Let's run the code. We have our results based on two tests of two proportions. So we submit and move on. So calculate the standard deviation for this using the equation. They calculate the p hat multiplied by 1 minus p1. That should give us p hat. That'll be 1 minus p hat. Then divide by the p hat times p hat by a number of reasonable rows and number of expensive rows. This is it. Let's run the code. Voila. Then we calculate the z-score using the following equation: p1, p expensive and p reasonable, to give us the z-score, which is the z-score here. Then nicely to call the p-value from the z-score. The p-value from the z-score, which is num.cdf, that will be num.cdf 1 minus num.cdf underscore z-score, to give us these results. Next is to get counts of the late column group by flight group. Let's see the results here. Let's say a number of solution. Yes, for the two. This is how you do that. Determine which the one number of each goes in each. Okay, I'm going to code. Should have a result by there. Chi-square.
Just as ANOVA extends t-tests to more than two groups, chi-square tests of independence extend proportion tests to more than two groups. Here's the proportions test from the last video. The test statistic is the z-score of minus 4.22. That proportion test had a positive result. The small p-value suggested that there was evidence that the hobbyist and age category variables had an association. If the proportion of hobbyists was the same for each age category, the variables would be considered statistically independent. More formally, two categorical variables are considered statistically independent when the proportion of successes in the response variable is the same across all categories of the explanatory variable. The Penguin package has an indirect way of testing the difference in the proportions from the previous video. To the chi-square independence method, we pass Stack Overflow as data, hobbyist as x, and agecat as y. The correction argument specifies whether or not to apply Yates's continuity correction, which is a fudge factor for when the sample size is very small and the degrees of freedom is 1. Since each group has over 100 observations, we don't need it here. The method returns 3 different pandas data frames: the expected counts, the observed counts, and statistics related to the test. Let's look at stats and focus on the Pearson test row and the chi-square and p-val columns. The p-value is the same as we had with the z-test of around 2 in 100,000. The chi-square value is the squared result of our z-score, seen in the previous video. Let's try another example. Recall that the Stack Overflow sample has an age category variable with 2 categories, and a job satisfaction variable with 5 categories. We can declare hypotheses to test for independence of these variables. Here, age category is the response variable, and job satisfaction is the explanatory variable. The null hypothesis is that independence occurs. Let's use a significance level of 0.1. The test statistic is denoted chi-square. It quantifies how far away the observed results are from the expected values if independence was true. Let's explore the data using a proportional stacked bar plot. We begin by calculating the proportions in each age group. Next, we use the unstack method to convert this table into wide format. Using the plot method and setting kind to bar and stack to true produces a proportional stacked bar plot. If the age category was independent of job satisfaction, the split between the age categories would be at the same height in each of the 5 bars. There's some variation here, but we'll need a chi-square independence test to determine whether it's a significant difference. Let's again use the chi-square independence test from Penguin. We have Stack Overflow as the data, and JobSat and AgeCat as x and y. We leave out a correction here, since our degrees of freedom is 4, calculated by subtracting 1 from each of the variable categories and multiplying. The p-value is 0.23, which is above the significance level we set, so we conclude that age categories are independent of job satisfaction. Swapping the variables so age category is the response and job satisfaction is the explanatory variable, we see that the splits for each bar are in similar places. If we run the chi-square test with the variables swapped, then the results are identical. Because of this, we phrase our questions as, are variables x and y independent? Rather than, is variable x independent from variable y? Since the order doesn't matter. We didn't worry about tails in this test, and in fact, the chi-square independence method doesn't have an alternative argument. This is because the chi-square test statistic is based on the square of observed and expected counts, and square numbers are non-negative. That means that chi-square tests tend to be right-tailed tests. Time for some practice.
Oh, network is okay. That's the answer. I say increase. When tails of Hokkaido this. No. Right now, the chi test is a square number, so it's always non-negative. So only the right tail test to be of interest. Performing a chi-square test, interesting. You can calculate the proportion of ferrite cost group in late shipment by vendor. That will be late shipment or goodbye vendor value count. We want the code. On stack, the value count results will be in the white format instead of long. Pub dot on stack. Okay. Let's say create a professional stack block part filled with very high costs and so wide proportion plots with a kind bar. That should show us the results. Then perform a chi-square test dependence on the Ferrari cost group and vendor income term in late shipment datasets. So that is the final part of the code. And finally, what should you conclude from the hypothesis test? That they feel oh the page is loading and loading. And so then inside the test compare. That's interesting. So we now have chi-square test of fits. Let's look at the chi-square goodness.
Last time, we used a chi-square test to compare proportions in two categorical variables. This time, we'll use another variant of the chi-square test to compare a single categorical variable to a hypothesized distribution. The Stack Overflow survey contains a fun question about how users feel when they discover that they already visited the top resource, also called a purple link, when trying to solve a coding problem. We can use the .value counts method to get the counts of each group in the purple link column. We also do a little bit of manipulation here to get a nicely structured data frame that we can work with later. First, we rename the leftmost column to be purple link, assign the counts to n, and finally sort by purple link so the responses are in alphabetical order. There are 4 possible answers stored in the purple link column. Let's hypothesize that half of the users in the population would respond, "Hello, old friend," and the other 3 responses would get 1/6 each. We can create a data frame for these hypothesized results from a dictionary of key value pairs for each response. We specify the hypotheses as whether or not the sample matches this hypothesized distribution. The test statistic, chi-squared, measures how far the observed sample distribution of proportions is from the hypothesized distribution. Let's set the significance level of 0.01. To visualize the purple link distribution, it will help to have the hypothesized counts for each answer, which are calculated by multiplying the hypothesized proportions by the total number of observations in the sample. Let's create a visualization to see how well the hypothesized counts appear to model the observed counts. The natural way to visualize the counts of a categorical variable is with a bar plot. First, we use plt.bar to plot the observed purple link counts, setting the horizontal axis to purple link and the vertical axis to n. We set the color of the bars and add a label for a legend. We do the same again for the hypothesized counts, but also add transparency with the alpha argument. We can see that two of the responses are reasonably well modeled by the hypothesized distribution, and another two appear quite different. But we'll need to run a hypothesis test to see if the difference is statistically significant. The one-sample chi-square test is called a goodness of fit test, as we're testing how well our hypothesized data fits the observed data. To run the test, we use the chi-square method from scipy.stats. There are two required arguments to chi-square: an array-like object for the observed counts, fobs, and one for the expected counts, fexp. The p-value returned by the function is very small, much lower than the significance level of 0.01. So we conclude that the sample distribution of proportions is different from the hypothesized distribution. Let's perform some chi-square goodness of fit tests.
Okay, cool. My camera is on go. Oh, serious. You check. Bye bye. Thank you. I come check on camera. Is it okay? I know. I said thank you. Now we come be on camera. What is? So it says to find total number of rows in list shipments. Okay, so lane the shipments, which is 199. Then add a column name n to be hypothesized, data frame that is hypothesized prop, so a total camera times in total times n total. So look at the code explanation. Interesting. Let's reload the page again. Then finally, it says create a bar graph when versus vendor income term for the income and data specifying a red color. Interesting. Let's submit our answer. Finally, observe as I hypothesize. But about two of the bars very close to the So using a term, so using the income count, I said that set up a chi-square goodness of fit on the income count. Oh, that should be chi-square income tax. Okay, will then definitely be fail to reject the null hypothesis or reject the null hypothesis for that. Fail to reject the null hypothesis and that conclude the n follows the distribution. What a goodness of fit. The test to compare the proportions of a categorical variable to hypothesize distribution is called a chi-square goodness of fit test. Okay. Hypothesis is quite strong and very, very technical. You need to be calm to get your hand around hypothesis in Python. Oh, this is loading and loading. Page is taking time to load. Okay, so let's move to the chapter 4, which is non-parametric tests in Python. Let's see what this is. Assumptions in hypothesis testing.
Each hypothesis test we've seen so far makes assumptions about the data. It's only when these assumptions are met that it is appropriate to use that hypothesis test. Whether it uses one or multiple samples, every hypothesis test assumes that each sample is randomly sourced from its population. If we don't have a random sample, then it won't be representative of the population. To check this assumption, we need to know where our data came from. There are no statistical or coding tests we can perform to check this. If in doubt, ask the people involved in data collection, or a domain expert that understands the population being sampled. Tests also assume that each observation is independent. There are some special cases, like paired t-tests, where dependencies between two samples are allowed, but these change the calculations, so we need to understand where such dependencies occur. As we saw with the paired t-test, not accounting for dependencies results in an increased chance of false negative and false positive errors. Not accounting for dependencies is a difficult problem to diagnose during analysis. Ideally, it needs to be discussed before data collection. Hypothesis tests also assume that our sample is large enough that the central limit theorem applies, and the sample distribution can be assumed to be normally distributed. Smaller samples incur greater uncertainty, which may mean that the central limit theorem does not apply, and the sampling distribution might not be normally distributed. The increased uncertainty of a small sample means we get wider confidence intervals on the parameter we are trying to estimate. If the central limit theorem does not apply, the calculations on the sample and any conclusions drawn from them could be nonsense, which increases the chance of false negative and false positive errors. How big our sample needs to be big enough depends on the test. For one sample t-tests, a popular heuristic is that we need at least 30 observations in our sample. For the two-sample case, or ANOVA, we need 30 observations from each group. That means we can't compensate for one minority group sample by making the majority group bigger. In the paired case, we need 30 pairs of observations. Sometimes we can get away with less than 30 in each of these tests. The important thing is that the null distribution appears normal. This is often the case at around 30, and that's the reason for this somewhat arbitrary threshold. For one-sample proportion tests, the sample is considered big enough if it contains at least 10 successes and 10 failures. Notice that if the probability of success is close to 0 or close to 1, then we need a bigger sample. In the two-sample case, we require 10 successes and 10 failures from each sample. The chi-square test is slightly more forgiving and only requires 5 successes and 5 failures in each group, rather than 10. One more check we can perform is to calculate a bootstrap distribution and visualize it with a histogram. If we don't see a bell-shaped normal curve, then one of the assumptions hasn't been met. In that case, we should revisit the data collection process and see if any of the 3 assumptions of randomness, independence, and sample size do not hold. Time to check some assumptions.
So let's look at the common assumption of hypothesis testing. Hypothesis test makes assumption about the data set that they are testing and the conclusion you draw from the test results. are only valid for use. Okay. As is assumption, all hypothesis tests assume that the data are collected at random from the population that actually is dependent of the others. Okay, so let's see. Get the count of its value. Okay. Now let's get the count of each value in the list column list shipment. Then we count and finally get the count of each value for right cost group. Then finally get the count of each shipment column of the list shipment. And voila. There's no non-parametric test.
So what do we do if the assumptions for the hypothesis tests we've seen so far aren't met? The tests that we've seen so far are known as parametric tests. Tests like the z-test, t-test, and ANOVA are all based on the assumption that the population is normally distributed. Parametric tests also require sample sizes that are big enough that the central limit theorem applies. Let's study a case where the sample size requirement isn't met, with a subset of the US presidential voting results for Republican candidates that we examined in a previous chapter. Here, Repub Vote Small contains only 5 counties, randomly sampled from the larger dataset of 2008 and 2012 county-level returns. Let's try performing a paired t-test on this small sample. Recall that we require 30 pairs to feel confident in using a t-test, and this sample only contains 5. We set a significance level of 1% and use the t-test method from Penguin to perform the left-tailed paired t-test. The small p-value indicates we should reject the null hypothesis, leading us to suspect that the 2008 election had a smaller percentage of Republican votes than the 2012 election. In situations where we aren't sure about these assumptions, or we are certain that the assumptions aren't met, we can use non-parametric tests. They do not make the normal distribution assumptions or the sample size conditions that we saw in the previous video. There are many different ways to perform tests without these parametric assumptions. In this chapter, we'll focus on those relating to ranks. Consider the list X. The first value of X, 1, is the smallest value, and the second value, 15, is the fifth smallest. These orderings from smallest to largest are known as the ranks of the elements of X. We can access them with the rank data method from scipy.stats. Let's now use a non-parametric test to see what kind of results it gives. Remember that non-parametric tests work better than the parametric alternative in situations where the sample size is small or the data cannot be assumed to be normally distributed. We will use the Wilcoxon signed rank test, which was developed by Frank Wilcoxon in 1945 and was one of the first non-parametric procedures developed. We'll go over the inner workings of the test before implementing it using another Penguin method. The Wilcoxon signed rank test requires us to calculate the absolute differences in the pairs of data and then rank them. First, we take the differences in the paired values. Next, we take the absolute value of the differences using the .abs method and place them in the absdiff column. Then, we rank these absolute differences using the rank data method from scipy.stats. The last part of our calculation involves calculating a test statistic called W. W uses the signs of the diff column to split the ranks into 2 groups, one for rows with negative differences and one for positive differences. T- is defined as the sum of the ranks with negative differences, and T+ is the sum of the ranks with positive differences. For this example, all the differences are negative, so the T- value is the sum of the 5 ranks, and T+ is 0. The test statistic W is the smaller of T- and T+, which in this case is 0. We can calculate W and its corresponding p-value using a penguin method instead of manual calculation. The dot-Wilcoxon method from Penguin takes very similar arguments to the dot-t-test method, except it doesn't have a paired argument. The function returns a W value of 0, the same as our manual calculation. This corresponds to a p-value of around 3%, which is over 10 times larger than the p-value from the t-test, so we should feel more confident with this result given the small sample size. The Wilcoxon test indicates that we do not have evidence that the 2008 Republican percentages are smaller than the 2012 percentages using this small sample size of 5 rows. Get your Wilcox on.
Oops, okay, let's say Wilcox in action. Which test is a parametric equivalent to the Wilcox sign text? That should be chi-quest of test or PIT test. The Wilcox sign rank test whole square when consumption of PIT test are intimate. Interesting. It now says conduct a peer test on the percentage column using the appropriate alternative text. Okay. The next is to conduct a Wilcox sign rank test on some columns. Just two selected columns to run the Wilcox PyChi test quest. Non-parametric ANOVA.
In the previous video, we explored some non-parametric techniques and how they compare to their parametric counterparts. We'll continue on that theme here, focusing on non-parametric alternatives to tests of independent numeric samples. We can avoid assumptions about normally distributed data by performing hypothesis tests on the ranks of a numeric input. The Wilcoxon-Mann-Whitney test is, very roughly speaking, a t-test on ranked data. This test is similar to the Wilcoxon test we saw in the last video, but works on unpaired data instead. Let's return to the Stack Overflow survey and the relationship between converted compensation and the age respondents began coding. We start by focusing on just those 2 columns in a new data frame called age versus comp. To conduct a Wilcoxon-Mann-Whitney test with Penguin, we first need to convert our data from long to wide format. This is accomplished with the pivot method from Pandas, which unlike pivot table does not aggregate. Instead, it returns the raw values for each group across the rows. We now have our data in 2 columns named adult and child, with the values corresponding to the converted comp entries for each row. An adult value of nan corresponds to a child entry, and a child value of nan corresponds to an adult entry. Let's set a significance level of 1%. We can run a Wilcoxon-Mann-Whitney test using MWU from Penguin. It accepts x and y arguments corresponding to the 2 columns of numbers we want to compare, in this case, child and adult. Alternative sets the type of alternative hypothesis, in this case, that those who code first as children have a higher income than those who code first as adults, which is a right-tailed test. Here, the p-value is shown as around 10 to the negative 19th power, which is significantly smaller than the significance level. In the same way that ANOVA extends t-tests to more than 2 groups, the Kruskal-Wallis test extends the Wilcoxon-Mann-Whitney test to more than 2 groups. That is, the Kruskal-Wallis test is a non-parametric version of ANOVA. We use the Kruskal method from Penguin to perform a Kruskal-Wallis test to investigate if there is a difference in converted comp between job satisfaction groups. Unlike the Wilcoxon-Mann-Whitney test, we don't need to pivot our data here, since the Kruskal method works on long data. We pass in stack overflow as data, the dependent variable dv as converted comp, and we are comparing between the groups of jobsat. Again, the p-value here is very small, and smaller than our significance level. This provides evidence that at least one of the mean compensation totals is different than the others across these 5 job satisfaction groups. You're almost there. Head on over to the exercises to give these tests a go.
Okay, so let's see the way comes man YT tests in action. So it says another class of non-parametric repetitive tests are called rank sum text, and we're calculating the rank of data instead of the actual values. You can avoid marking as option. So select weight of kilograms and lead from the late shipment assigning and weight column. Select those columns. They try to make more. They try to make me use parameters, but I said no. The same p-value leads us to suspect that difference does exist in the weight of shipments. Using another type of test, then it just says run a causal all these tests on weight kilograms between the different shipments and the late shipments, between shipment and late shipments. Interesting. It's okay. Oh, that's quite technical. A lot of technicalities there.
Well done. You've made it to the end of the course. To recap, in Chapter 1, we learned the workflow for testing proportions against a hypothesized value. We calculated the observed statistic and a z-score, then transformed the z-score to get a p-value. We also learned about false negative and false positive errors. In Chapter 2, we learned how to test for differences in means between 2 groups using t-tests, and how to extend this to more than 2 groups using ANOVA and pairwise t-tests. In Chapter 3, we returned to proportion responses and learned how to test for differences in proportions between 2 groups using proportion tests. We then extended it to more than 2 groups with chi-square independence tests, and returned to the one sample case with chi-square goodness of fit tests. In Chapter 4, we learned about the assumptions made by parametric hypothesis tests, and saw how non-parametric tests can be used when those assumptions aren't met. Hypothesis testing is part of a branch of statistics known as inference. DataCamp has more courses that delve deeper into inference. The techniques used in this course are an example of frequentist statistics. A rival paradigm is known as Bayesian statistics, and naturally, DataCamp has a course that teaches it. This course began with an example of A/B testing, which is a common use case for hypothesis testing. You can learn more about A/B testing in this course. Congratulations for completing the course. I wish you the best of luck on your data journey.
All right, thank you. I wish you some best of luck. All right, so that'll be the end of hypothesis testing in Python. So just download the data set in the YouTube description so you can also practice and know all the technicalities. I'll see you in the next live stream lesson.